So let's continue with what we did last time. So we looked at MapReduce, we looked at the matrix multiplication example, we looked at a sort of a n-square algorithm of comparing the similarities between images and using that to cluster it. And we basically started looking at evaluating the complexity of MapReduce algorithms. We are sort of going to continue with that, and then we'll start looking at PageRank, which, as I mentioned earlier, would be your next assignment. So when we talk about MapReduce, the complexity for MapReduce, we talked about these two. This is a repeat from last week's lecture. I just want to remind you again, for those of you who don't remember it, that we try to characterize our algorithms using the reducer size, which is an upper bound on the number of values that any given reducer can receive corresponding to a single key. And that's sort of an indication of the level of parallelism that the algorithm exposes for us. The other aspect is, of course, the replication rate. And when we get to the next slide, it will become a little bit clear. But replication rate, this is something which we don't really consider or didn't consider when we talk about MPI algorithms, because there is a lot of flexibility of doing things in a parallel fashion inherently. Because in MPI, we are sort of limited to these, in MapReduce, we're limited to these sort of a two-stage affair of having a map and a reduce. In many cases, the way of obtaining this level of parallelism is to have additional replication or having redundant replication of data. And so this is an indicator for how much communication we involve. So this is basically, it's the number of key value pairs produced by all the map tasks put together divided by the total number of inputs. So this is sort of, remember that we talked about the complexity being measured in terms of the input to any of the stages. And the output of the map is the input to the reduce stage. So we are basically, this is an indicator of how much additional or how large the input has grown with regards to the input size as you pass it through the map stage. Look at the graph model here, right? These are the inputs, these are the outputs, correct? Qi is the number of inputs at each of the reducers, correct? So when I sum over all of these, that is the total amount of data exchanged between all the inputs and all the outputs, okay? So all I'm doing is I'm summing over the number of inputs on all the reducers, okay? That's all we're doing. It's not very complicated. It's just if you look at the steps, it becomes a little bit clearer on what we're doing. Is it clear or no? Yes.
So basically, each reducer is in charge of one block of that matrix, right?
Which matrix?
The matrix on the board.
Well, in this case, we're trying to analyze this independent of whether it's a block or whether you're doing a pair. We're just trying to say that we're only trying to look at the input and the output relationship to figure out what the best, the minimum amount of communication that would be required if you had to do it with a single map and a single reduce stage are.
Yes, I mean, in this case, each reducer is compute for one block.
Yes, it's looking at some block out here, yes.
So that Q squared over 2, the exact number should be Q times Q plus 1 over 2, right?
Yes, so that's why I said Q choose 2, which is basically Q factorial by 2 factorial, Q minus 2 factorial, right? So that's Q minus 1 by 2. I'm just approximating it so that we have a nicer expression which we can simplify out here. But yes, that's the case. Anything else? Let's look at one more case of this. So let's look at this is one reducer. The output is, try to think of the analysis that we just did. The output is n over g squared, but the input is n times n over g from each of these matrices. So it's 2 n squared over g. See this, if it should be clear from this, right? Yeah, this is greater than or equal to, but what we computed in that case, that algorithm gives us the lower bound as well. That is the upper bound and the lower bound. So yeah, you can, R is equal to this is greater than or equal to, yes. Okay? So, but let's now revisit the two-pass approach. When we first looked at matrix multiplication, we sort of ignored, we moved quickly past the two-pass method. You remember the two-pass method? We were not, the replication rate was not n, we were generating one key per element, but we had to do two MapReduce stages to compute the matrix multiplication, right? Let's analyze this and see if this is actually going to be better than doing the one-pass approach. So, n by n matrix with entries mij. This is the same thing. I think I just copied the old one. Yeah, this is the old slide. So this is, in this case, we have to group it in a more complicated fashion. We're going to again go for a grouping, but we're going to use blocks. Okay? In the first stages, the product of these blocks is computed, and then they are summed up together to produce the result in the second pass, right? You remember that, right? First pass, compute product of square ij of m with square jk of n, and then second pass, sum over all ik and sum over all j. For all ik, sum over all the j combinations to generate the output out here, okay? We're going to have g square groups of n square over g square elements each, right? So there, when we considered the one-pass algorithm, we were only reducing the groups in one dimension. They were all still, so remember there we had 2n square over g. Here we're going to have 2n square g square over g square, okay? So that's sort of the case where we are going to get some reduction. So, what is the replication rate for map 1, the first map? Is G, right? Each key has to be now sent to the G different groups. So there's a total of 2G n square total communication. There are two matrices of n square each, and each key is replicated G times. Correct? Each reducer gets 2n square over G square entries, right? Those are the values that you get, which is basically your Q. That's the reducer size, which means that G can be expressed with this expression N2 over Q, which means that the total communication is this, which is basically this times that. I just plug in the expression for G in the above expression so that I can get an estimate for the total communication in terms of N and Q. So this is, we have not yet done the method independent, the graph-based analysis for this. What does this number tell you? This expression in terms of the complexity compared to the two-pass method, the one-pass method. So that was n to the power 4 over q. This is n cube over square root of q. Okay? So this is, and we'll look at what it really means, but fundamentally it's going to depend on the relationship between n and q to some extent. And you should know where it's going. If map2 runs on the same nodes as reduce 1, which is not unlikely, there's no extra communication involved out here. The only communication would be from map2 to reduce 2, which is going to be gn square, because we already computed the blocks and we're just summing up over each of those groups. So that's gn square, which is this expression. So that this is exactly half of the first one, and it makes sense. We had two inputs which we were multiplying together, and now we're just summing over these. So the total communication is 3 square root of 2 n cube over square root of q. Is this clear? What is 3? So you can analyze this, and you can, maybe I'll give it as an assignment. If you choose a slightly different partitioning scheme out here, this constant can be reduced a little bit further. So instead of 3 square root of 2, you can get 4. And this is just marginally over 4. Move on to page rank. Is this clear?
Why was that number 2, like, was it significant to
2n.
2n, so that's what I just explained, right? So consider the problem of matrix multiplication. If I have to generate, a reducer has to generate at least one output. And let's say the output is just a single entry in the output matrix. So what is the minimum amount for Q? What is the minimum number of inputs that I need at a reducer to produce at least that one output? Would be one row of matrix M and one column of N. So that is 2n. So that's why, so Q cannot be less than 2n because of that limitation. And if we go for that situation that we have the smallest reducer size possible, which might not be the optimal thing to do anyway, right? We already said that this is what is more realistic because you're not going to do it. So it's going to be basically between 2n and n square is where you're going to operate, right? If we bring it down to this, then you're getting a reduction out here. Remember also that's why I was saying that the constants are also sort of important here. We had 4n, 4 over q here, and this was 3 square root of 2, the way we did it. Which is a slight difference, but you can get the constants here as well down to 4. But fundamentally, this is what is saying that although you have extra overhead in terms of having two MapReduce stages for the 2-pass algorithm, from a complexity perspective, it makes more sense to do the 2-pass approach. And when you guys implement PageRank, well, you don't need to do this, that's okay, sorry, ignore it. I'll give it to you specifically as an assignment. Implement both of these to see how much of a difference it makes in a realistic scenario. They're not that hard to implement, so you can look at the numbers and see how much of this scales out. Are you actually seeing the same kind of scalability curves for each of those algorithms in terms of being n to the power 4 over q and so on? Okay? Clear? Should I move on? Okay. So now that we've sort of done some of the basic stuff, let's get on to interesting problems. For the duration of this, let's think it's late 90s and early 2000s. So we're going to start off with Google. A lot of the work, and we're going to be looking at a bunch of other papers by Google as time goes by, but we sort of, let's go back to the start. And I don't know how many of you remember early days of search before Google sort of came into the picture. You had Alta Vista, yes, exactly. And don't even, Yahoo was there as well. So how do you remember, so do you know what happened that time? How were searches being performed? How were you searching websites, and why did it not work? So you need to sort of understand that the mathematics behind PageRank is actually fairly simple, so it won't take time, but you need to appreciate where Google, this is sort of one of the early papers from the founders of Google, so this is what they worked on and why it was a clever idea. So what people like Alta Vista and most of the other search engines at that time used to do is that they would create a inverted lookup table between keywords to URLs. So you would go ahead, you would have a crawler like what you guys wrote, but you would basically try to create the reverse mapping. Right now you know that given a URL you have maybe somewhere stored on disk the pages, but you can extract a bunch of only the keywords, let's say. And you can sort of try to make this as complicated as you want. But the general idea was that when you did a search, you're going to search for a bunch of keywords. It's going to look in this inverted map and see which pages have them, and then try to use heuristics to get to rank these pages. So you're not, when it comes to the part of doing the actual search, you've looked at the inverted mapping, figured out that these are these few hundred pages which have these words, and now I'm going to somehow look at only these pages to figure out if they're good. And if you remember, it was very difficult to find stuff because if you're interested in scamming or spamming somebody, then you put the keywords. People are looking for, I don't know, they're looking for lectures, and they say, oh, this guy's lectures here, buy my stuff. Because fundamentally, you want to make sure that your page shows up in one of these inverted maps, and then you can reverse engineer the heuristic that the search engine is using to make sure that you end up on the top, which could be as simple as just going to the top guy on the search, copying his HTML page code, dumping it in there and hiding it, maybe changing the color or something, making sure your text is as close to the top guy, which means that you're going to show up, even though it's junk otherwise, right? So what is the problem with this approach? It seems okay. How do you, if you were to get into this sort of an approach, what is the fundamental thing? That the ranking, to some extent, of how you're figuring it out is still based on content that you have control over, which means that it makes it easy for you to modify your web page to make sure that it goes up, right? And over the years, we're going to look at PageRank. I doubt if Google is still using it. They have probably evolved the algorithm, because in most cases, you're going to, people are going to try to, reverse engineer the system if they don't, even if they don't know about it, and try to figure out ways to circumvent whatever checks are there to avoid these kind of fake results from showing up. So what PageRank does is to say that we're going to do it the other way around, which is that let's try to figure out or assign an importance to a particular web page, not based on what you are claiming is there. The inverted lookup table will still be there to make sure that you have the words, but I want to now rank them not based on necessarily things that they have claimed, but by how popular this is otherwise, right? So the general impression being that if you have links to you from your web page from cs.utah.edu, then you're probably a little bit more credible than if you don't have anybody linking to your page, right? And so there are different ways of doing it. Formally, the definition we've sort of talked about this, I think, sorry. Yeah, so the key idea was that you want to have a high quality web page. So when you search, there are going to be millions of pages which might have the keywords that you're looking for, but it's still an issue of presenting it in the right order so that your top hits are what you're really interested in, not the junk which has been filled out there. And actually, the approach that what's the other guy's? Brin, and who's the other guy? Larry Page. Yes. Okay. So what they came out with was actually based off research at that point, which existed for figuring out high quality scientific publications. So for those of you who might have considered or written papers, you'll see that citations are important, and that's the basic idea that if your paper is being cited by a lot of people, then you've done something noteworthy at least, because others think that you're good, rather than you claiming that you're good. And that's the general idea. And in this case, the idea is that if you have links from your web page, so let's say you read a blog, right? You can think in terms of one day that somebody writes a nice news article and it has, let's say, 1 million Facebook likes, or it gets tweeted a few million times. That's a good indicator of that others think it's good. And that might be something that you want to bring up on your search list. And it's the same general idea. And it's harder to cheat the system because you don't have control to modify somebody else's web page. People do that. You can create fake web pages, all of them linking to you. But then there are ways to check that out. And so you can say that, if New York Times is linking to you, then it's more credible than some unknown web page out there. So let's sort of look at a simplified scenario out here, right? So assume that the internet has only 4 web pages, and these arrows out here show where links exist from one page to the other. So if you're on page A, pages B, C, and D are there as links. and from B you only have links to A and D, from A and D to C. There's no link from B to C and so on. So this is sort of representative of it. So when you guys wrote your crawlers, you were generating this data, but one way to look at it is to actually generate a graph of this sort, of where each node is a particular web page and where the links are. So we talked about this importance, but there is another way of looking at it, is saying that let's consider that we have a set of random web servers or crawlers, and they're just going around arbitrarily spending time on all of these web pages. Then you want to estimate the probability that this particular random browser or crawler is on a given page, right? So think of it in terms of highways or roads and the way you are driving, right? So the major roads, which are in densely populated areas, it's more likely that somebody is on one of those rather than some small residential street somewhere. So the more popular, the more the links, the higher the probability that you're going to end up in that particular page. And so if the probability of a random browser or a crawler of sorts ending up on a page is high, then that page must be important, because the probability is going to, and this is sort of, it cumulates, right? So there is a high probability that you will end up, the random browser, on, say, Yahoo or New York Times as opposed to, I don't know, foobar.com, right? Then the probability, if one of these very likely websites, it is high importance website, link to me, then I am important as well, because they transfer that probability onto me. The chance that, so they get a lot of traffic, which means that the probability of me getting a lot of traffic is also high. Make sense? And that's fundamentally what it is. But the question is, how do you actually estimate these probabilities? So given the structure of the graph, and now you need to look at this example, but I want you to imagine the whole World Wide Web and the massive billion by billion graph that you would sort of end up with. And I managed to find a good data set for you guys. It's a snapshot of the web from 2001. So it's sort of close enough to what these guys would have tried it on. So I want you to sort of figure out the importance of the pages from that era. So what you're going to have is, you can think of it as a matrix where these are, let's say, the web pages, and then we are looking at probabilities, which we assume that if a link exists, there is a uniform chance that you will click on every one of them. We're not getting yet into the quality of those links itself, which might be the case. You can think of it if you were doing some keyword specific probability, then these might depend on the kind of keywords that you found next to the links that we are talking about. So from node A or page A, the probability, we are ignoring self links for now, so the diagonal is going to be 0. We can factor that in if required. But because A has 3 edges to all the other pages, the probability that a random user is going to click on any of them is going to be equal, and it's going to be 1 over 3, right? Similarly, from B, I can end up with equal probability on either A or D. So A and D get 1 over 2, and there is 0 probability that I end up on C or B again. Similarly, from C, I can only end up on A with probability 1, and it's 0 otherwise, and finally for D as well. Okay? Is this clear? Now, if we say this, right, that this is my transition matrix, which is it's sort of encoding the structure of the web. We can define a variable V, which is the probability distribution for the location of a random surfer. This is the same definition that we gave for the page rank, because this is the probability that somebody is on a given web page, reflecting the importance of that page, which is what they refer to as page rank. if you start off with an initial guess, which is equal probability that this vector is on, that the surfer is on any of these web pages, and we iterate repeatedly using the transition matrix, this is going to eventually converge onto the correct, the steady state solution. So that's going to result in the limiting probability for this particular graph. Okay? That's because this is basically, fundamentally, it's a Markov process where we have said that this is a given set of states and these are the probabilities of transition on to the next state, right? And what we are interested in is the limiting distribution or the steady state solution for this. It will converge, and there are proofs for this. I can point you to textbooks if you want. But that's only if the underlying graph is strongly connected and there are no dead ends, okay? Because otherwise, if you have dead ends, then it's a sink. So with a very high probability, it's like Hotel California, right? You can check out, but you can't leave. So you're just coming in, and that's it. So the limiting distribution in the case of a dead end is going to be that everybody is going to end up on the dead ends, right? Which is not what we want. The dead ends are not the important pages. Mathematically, the limiting distribution V is basically an eigenvector of this matrix M. Okay? And for those of you who have taken a scientific computing course or numerical analysis or basic linear algebra, I guess, this is an eigenvalue problem. And you can see that we are basically solving for the principal eigenvector in this case. In this case, because the rows and the columns of the vector add up to 1 because of the probabilistic definition, V is also the primary eigenvector because the largest eigenvalue is 1. And that's what we are iteratively solving for, right? So the iterative way of doing this is like the cheapo power iteration method in some sense because of the structure that we have assumed for our transition matrix, okay? And you will see that a lot of these large problems can easily be mapped onto traditional linear algebra problems. So fundamentally what you're doing is you would set up this transition matrix. So you look at your crawler data, build a graph in a matrix form, and you're going to iterate on this till you converge within some tolerance, right? It's basically that additional iterations do not reduce the error any further, which means that you've converged, okay? Typically, even for these large cases, 50, 60 iterations should actually converge to pretty close to machine precision. It's a relatively easier problem because of the nice structure, if you do not consider these cases.
So if in some sense the rank would be lambda, so would it be
What rank?
the rank here?
Rank of what? The
Rank of
matrix?
page.
Oh, it's V.
It's V.
It's V that you're solving for, right? It's the primary eigenvector is basically giving you the importance of this. Okay? Yeah?
Vector, right?
Yes. It's a vector of size n, and there are n pages. The value of each of them gives you what the value is.
Okay.
Right? It sums up to 1.
Yeah.
So,
But it gives you
you're more likely to be on Google than you're likely to be on some random website. So that's probably getting a bigger, it's less than 1, but it's probably the largest of all of them. So that distribution basically tells you on which page you're likely to be. So the more likely a random guy is to be on a page, the more likely that you, as somebody who's searching, are actually interested in looking at that page. So what Google would do would be to do the search. Once it gets the results, it's going to rank them by these, and that's why the page rank definition comes in. This is not, in the earliest versions, it wasn't changing necessarily what was being brought up. It was just what is the best thing to present to the user. Because if you search for, why not, cats, you're going to get, a million, billion pages. How do you figure out which one should really be presented? The first 10 is what you're probably going to look at. So if you, to avoid junk, you want to look at this, and that's what this is doing, right? It's giving a sort of a global importance, right? It's an eigenvector, right? So you're solving a coupled problem. So it's difficult for somebody to make local changes to their problem or to their web page and make sure that it ends up on the top. Okay? Yeah, a little bit of time. This sort of also leads up. I'm not going to go very deep into this. We're only going to look at some simpler systems out here, but it brings up this issue that you basically have to solve a linear system in some sense, right? So a linear system here would be solving some equation of the mx equal to y types. In this case, it's an eigenvalue problem. And that requires some kind of an inversion of a matrix. And all of these are difficult. Now, for those of you who might remember from high school or I don't know when you guys did, but if you do Gaussian elimination, which is how you would do for smaller problems. So for the 4x4 matrix that we had here, we can do that by hand. And it's not too difficult, but it ends up being order n cube, and doing it in parallel is not really that easy, okay? Because of the causality that is introduced. Because what are you doing? You're going row by row and eliminating the values and making sure that the lower triangular is 0, right? So that is order n cube and is difficult to parallelize. That's why you opt for iterative approaches. When you look at iterative approaches, that's the method that we talked about here, where you're repeatedly applying m times v and trying to reduce the error. The complexity is going to be kn square, right? Why kn square? Here k is the number of iterations that you would take to converge, right? So I'm saying 50, 60 for the web, but in a general sense, you might not know how many iterations it's going to take. Do you see why it's n square? N square is the number of entries in your matrix. So n is the size of v, which is n. So the matrix is n square, and you need to multiply it with everything. That will be kn square. And now that's pretty expensive as well, right? Luckily for us, in most cases, when we deal with large cases, we're dealing with sparse systems. The web is also sparse. So there might be a few pages which have like a few hundred links, but most web pages are going to have a small number of links, which means that most of this matrix is going to look empty. It's going to be 0 because the chance of you ending up from any given web page to most of the other web pages is going to be 0, right? So it's sparse. So if it is sparse, you're going to get another constant now. I didn't add it, I'm just clubbing it up with k. But typically you're going to have some k times the number of non-zeros basically in the matrix. That is what is important. And you will see that typically for sufficiently sparse systems, the number of non-zeros is going to be equal to n. So that's not too bad. Iterative is nice because it's easy to parallelize, and as long as the systems are sparse, as in this case, you're going to get the optimal complexity as well. One thing which we are not talking about here, later in the class I'll bring it in. It's less relevant for big data, a little bit much more important, and in this case it probably is, as you will see, is to use optimal solvers or optimal complexity solvers. The importance here is that in many cases, the number of iterations that iterative methods, the choice of the iterative method, can take or to converge to sufficient accuracy is not independent of n. So as the size of the matrix increases, the number of iterations it takes for you to converge also goes up. There are some methods which will give you optimal convergence independent of size n. Those are more complicated methods, but those are the ones that you should ideally use for many of these problems. These are problems which will make use of the structure of the matrix to help you speed up. And so in that case, you can, irrespective of the size of the problem, get convergence in order n. Okay? So let's get back to solving it. I'll go very quickly through this because we're almost out of time. So the structure of the web, and this is probably way more complicated right now, is that there is a strongly connected component. These are the usual websites that you visit, which are all linked to each other. So there are no dead ends here, everybody is nice, everybody is connected to each other, which means that you can get from Google to New York Times and from there to BBC and back, no problem. All connections, all paths exist. In addition, you have like in components, basically parts of the web which will link into the strongly connected part, but there are no backlinks out. And similarly, there are parts which are linked out from the strongly connected part, but will not link back in. There are additional connections. So there is weird structure within the overall graph. You will also have completely disconnected parts. These could be, let's say, websites in some particular local language. These could be parts of the sort of the dark web where nefarious activities are going on and they are completely isolated from traditional websites, and you won't be able to search and get in here, and you have to know what it is, and it's sort of like a separate microcosm within the internet. Of course, we want PageRank to work, so we might end up with some of these. Now, this is going to be that you might not end up here if you're doing random crawling, but you will get all of these because you'll still be able to crawl. You'll be able to crawl and get all the way to a dead end, especially if you are parallelized it well enough, right? So fundamentally, when you think in terms of PageRank, there are two issues that we have to be careful about. One is dead ends, we talked about this. The other is spider traps, and some of you might have experienced this when you were writing the crawler. And they're called spider traps in the sense because it's a place where crawlers get stuck or spiders get stuck as they're crawling the web. What it is it's a connected segment of, a strongly connected component which only is connected from the rest of the web and has a way in but no way out. So you go in there, dead links could be ignored because you'll say, there are no links in this page, I'm going to go back and crawl the other way. But here you would constantly keep going around in circle with no way out. And it's harder to detect because some of these could be, so maybe you enter some corporate website which has links to internal documents but no links outside the corporation. And so then you're there with a million web pages which are completely in that area, right? Now, if you think in terms of, again, what will happen if we did the PageRank as we talked about, you're going to get completely stuck in there.
But eventually there will be a dead end, right?
No, there won't be. So imagine our curve. So if this was some, so if you had this, it's a loop sort of a thing.
What happens in practice is that you never see the entire web. So.
Yeah.
Right.
So
Never see.
this is what happens in practice. Google has to stop at certain point.
Of course. That's why you guys are going to be working with the 2001 data set and not something more contemporary.
Actually, there's like a paper saying that the more web you crawl, the more new things you see. So it's not like the more you're going to crawl, the less you're going to see. The less new things you're going to see. It's actually the more you're going to see. I think it's doubling or something like that.
Doubling?
It's doubling. So if I read n pages, I'll have 2n new bits. Even after I crawl like for a few days.
No, sure, of course. It will, but this is not only related to crawling, this is related to the PageRank part. Crawling has some issues, I'm giving you an example. So, couple of minutes, I'll just very quickly wrap up because it's easy. So the first case with dead ends is that we can just remove them from the graph, compute the PageRank as we thought about it, and then go back. We are kind of violating the official definition of probability, so they won't add up to 1. But we can use the probability of nodes connected to these dead nodes that we removed earlier and figure out the probability. So transfer the probability from the parts connected to the dead ends, which are part of the connected component part. Okay, I mean the major part without the dead end. That is an easy approach. The more generic approach would be to use something known as taxation, which is a slight modification to the expression where we originally had only v is equal to mv. Now we are adding a probability that beyond just following links, think of how you would browse. You get stuck somewhere, you go back to the address bar and you go somewhere else, right? So we are sort of bringing in this option that you're not only following the links, but there is a finite probability that you can randomly jump to some other website. And this allows you to get out of the trap, right? There are mathematical implications of this which I can discuss next time, but fundamentally you're defining some constant probability that you are going to follow one of the links, and 1 minus that times you're going to jump to a random web page in the overall domain, right? And then you can solve this now because you're not going to get trapped. The system is still going to be somewhat biased, so this approach will still be biased, and it's going to be also sensitive to the value that you choose for beta. So by making beta larger and larger, you're going to increase the bias that it's going to have towards the getting trapped in or giving higher weightage or higher page ranks to these kind of spider traps, because that part is going to have a greater significance. If you make it smaller, it's just going to take you very, very long to solve the system. So in this case, I talked about the size of the system and the number of iterations it takes being sensitive or being a function typically for many simple approaches to the size of the matrix. In reality, it's actually related to the condition number of the matrix as well. And different approaches have different relationship based on the condition number and the size of the problem and how they relate to each other. In this case, you're basically making it somewhat poorly conditioned, and that is going to increase the number of iterations it's going to take for you to converge there. So that is the reason why you won't make it very small. You will eventually get there, but it's going to take you too long to solve. So I think typically 0.8, 0.9 is what people end up using, which makes it still biased towards these. So we'll follow up next time. We'll look at more details on how some of these, there are additional approaches to fix these issues and what more modern approaches are for handling this.